And hello from the campus of Carnegie Mellon University in Pittsburgh, Pennsylvania. We welcome you to today's SCI webcast, Model Your Way to Better Cybersecurity. My name is Shane McGraw, Outreach Team Lead here at the Software Engineering Institute, and I'd like to thank you for attending. We want to make today's webcast as interactive as possible, so we will address questions throughout the webcast and again at the end of the presentation. And you can submit those questions now in the YouTube chat area. As I mentioned, we'll get to as many as we can. We also had several questions sent to us prior to the webcast, and we will work in some of those as well. Now I'd like to introduce our featured speakers for today. Natasha Shevchenko is a senior member of the technical staff within the CERT division here at the SCI. She specializes in systems engineering, enterprise architecture, model-based systems engineering, and threat modeling methods. She has a breadth of experience across the software development lifecycle for more than 20 years. Alex Vesey is a member of the technical staff also in our CERT division here at the SCI. His work focuses on the application of model-based systems engineering, threat modeling methodologies, and best practices in API design. Welcome, Natasha and Alex. Thanks for joining us today. Natasha, I'm going to turn it over to you for first remarks.
Okay, thank you, everyone. We will talk about MBSE and threat modeling today. I would like to start with a little bit of basics. What is MBSE? It's a new formalized, relatively new formalized methodology that came to focus several years ago, and right now making its way to a lot of organizations, programs, and universities. It is formalized methodology covering whole systems development life cycle, but it has nuances. And these nuances is, first of all, related to model-based character of it, which implied that formality comes from different aspects. I would like to touch that it's, first of all, it's standardized model and language. System engineering before was concentrated mostly on the process and did not provide any modeling, standardized model and language. First attempts to work on model and languages was started in 90s with UML, but right now without standardized model and language, you can't build any models, especially MBSE models. Second aspect, very important, it's these models need to be built in digital modeling environments. It's not paper-based, it's not document-based anymore. With complexity of our systems, size of our systems, we need help of computers everywhere, including design and system engineering. So this is a second very important aspect of system model engineering. You cannot do it in a document. Another is yes, it's system engineering process, but because it's digital based, it's model based, it's standard, it has standard model and language. The processes that it's used for system engineering need to be modified in accordance with that. And without that, you kind of encoding the old problems. With that, we probably can talk about this a bit more, but it's required another hour-long topic to talk about that. So other aspects like models, built for purpose, or portfolio executed models, it's true for other model-based approaches, and of course, MBSE include that. I want to touch on what is executable model. Executable model, it's one that you can run an analysis on it. It can be done with the help of modeling environment, or you will need to create additional maybe scripts, maybe programs that will implement the analysis based on the model you created. So if the models are not executable, their purpose will be diminished, their value will be diminished. Otherwise, it's become the overgrown documentation. So this is a critical one. Sometimes it's easier to identify something, define something based on what it's not. So that's why I want to touch what MBSE is not. MBSE is not about diagrams. Diagrams is a flat, you can say like two-dimensional views on some aspects of a system. It can provide some additional like details, technical details can be very helpful, but diagrams are not model. Again, MBSE, it's not just about tools. If you have a Cameo, doesn't mean, and you use the Cameo to draw diagrams, doesn't mean that you are practicing MBSE. It's one of the mistakes people does in the very beginning, saying that, oh, I have a tool, that's it. I am doing MBSE. Another similar problem is it's that MBSE, it's not only about modeling language. Yes, you can use SysML, but still you need processes, you need the executable models and other aspects to actually practice MBSE as a methodology. As I mentioned, we need to enhance system engineering processes to effectively practice MBSE. And again, if your system engineering process is right now document based, and you just was mandated to use MBSE, or really want to mention that, okay, I use MBSE because it's hot right now, and you just use it as creating the diagrams for your document process, you won't get any value. You will spend a lot of money on the tools and training of the people, and will have like minimum benefit from it. So this is like, I tried to summarize it in the very end, is that yes, MBSE not quick fix in any way. It's take time, it takes money, but if it's implemented correctly, with a strategy in mind, it can be a game changer. And now we try to emphasize why it can be a game changer for example, for cybersecurity. So next point I want to make, why the diagram is not enough. I got quite a few questions, and sometimes as a reply to my blogs or my other presentation, I have a drawing on the whiteboard. Why it's not a model? I have a model just because I did it, and I wouldn't say that it's why it's not. So there is sketches. It can be very helpful to convey additional idea. You can use a diagram if for somebody's like smaller programs, smaller software. Maybe a diagram will be more than enough. This is true because it's give you the details. But if you have a complex system and you need to analyze it, you have multidimensional aspects, security, networking, deployment, diverse of your workforce, and so on and so forth. You need a model which give you interconnection with the of the views, multiple views, specifically for different domain within your system, different stakeholders in your system. So if you don't have the size of a system like that, maybe you don't need full-blown MBSE. Maybe diagrams is good enough, but you need to think about that. Like, do you want to add anything?
Yeah, so while we're on the topic of diagrams, we're going to talk later in the presentation about threat modeling. And a lot of different threat modeling processes are diagram-based. But one of the things that we'll hopefully show later is that you don't necessarily need to throw out your favorite threat modeling process just because it is currently based on diagrams. We're hopefully going to show how you can adapt those processes to use more of the model views and hopefully be able to speed up and actually do slightly deeper analysis because of the enriched model views instead of trying to get that same kind of information out of diagrams. So, like I said, little bit of foreshadowing, but hopefully we can convey that.
Yes, very good. So let's touch a little bit about what is MBSE model specifically, not the methods in general, not methodology, but MBSE model. MBSE, not every model is MBSE model, even if it's kind of in a computer. So it's kind of digital model. So it needs to be made with a standard modeling language. One of them is currently most used. It's SysML. Some programs, some companies use UML. It's less formal than SysML, but it's pretty good for something. It's pretty good too. There is other languages like UFML or RAML that is based on SysML. Here in SEI, the ADL language architecture analysis description language is right now transitioned into SysML, which is again pretty formalized and standard language right now. So one of the reasons why you need it, because other models, with other companies or within your program is written in the same language, you kind of speak in the same language, right? So data and views and ontologies can go between models and between programs. They can understand each other better because they use one standardized language. Digital environment helps a lot with visualization, with creating the model, with visualization of the model, creating the views, also with version and configuration control of the models, because sometimes one model is not enough. You need federation of models, and it's required governance. And again, digital environment, it's very helpful for that. Architecture and design process. MBSE itself does not dictate the architecture process, but if your model, not creating of the model, not follow any formal language, process, it's becoming just a bunch of diagrams. So it's need a structure within the model, it's need a purpose and way of reasoning. And of course, again, it's executability, analysis need to be run in it, otherwise it's not MBSE model.
Quick audience question, Natasha. Is there, from David asking, is there a taxonomy that brings together these languages?
It's not that much taxonomy, but there is information that's showing the history of the languages, how they come together, how the SysML v1 is based on UML and expanded it a little bit. Very good source for that. It's website of OMG. It's its abbreviation. It's an organization that creates and manages standards for UML, for SysML, and other extensions to SysML. So it's Object Management Group. It's international standard organization. I really recommend people go there, and they will find all necessary information about the modeling languages. Okay, this is a big one. I'm sorry for being like eye chart, but I want to kind of convey a lot of information here. I'm trying to switch to move to security analysis, cybersecurity aspect in MBSE. So MBSE, its method and its underneath is system engineer process that cover whole life cycle, and you will need to create the models during each cycle of life cycle, create or modify or use some kind of model, one or several. So in the very beginning, you create the requirements model that during architecture, you will have number of different architecture models that feed each other, complement each other, and they will be extended by the solution models and deployment models, tested models. And on each level, you can run simulation on them if you want to. And it should be, you should think about traceability from the beginning to the end. So in the end, you should be able to exactly say if your requirements is satisfied, where specifically, how, if it's tested, when it's tested, how it should be tested. But where is the security comes in the picture? And right now, unfortunately, very often security start to address close to the end of the life cycle during development, like at the DevSecOps stage. And it can be very helpful, for example, if it's static or dynamic analysis of a code, or you introduce the monitoring features on your system, and so on. But very often for some vulnerabilities, for some problems, it's a little bit too late. They already coded and designed into your system. So the more proactive role of cybersecurity analysis, it's kind of required for, especially for a bigger system. You need to start early. And the best idea is the best way is to start when you just form your requirements for a system and talk about security requirements and your regulation, if any, the standards that your system need to follow. And very often they contain cybersecurity aspects. And this is where the MBSE can start to be very helpful, because you can document your requirements and engineer your requirements, including cybersecurity requirements, and start to make sure that they addressed by the design and architecture and design. On the next level, when you start already building your list of capabilities that you need to implement, or you work on your conceptual logical architecture, this is where first type of security analysis can be run, including risk analysis and threat modeling. So even traditional threat modeling done or threat happened when the detailed design already created for the system, it can be run much earlier with a lot of benefits, looking into inherent threats, looking into security risks. So, Alex, for sometimes already, you're working with threat modeling on early stages of software development. What you can say?
Right. So again, the earlier that you can start to identify those threats, right, the easier it's probably going to be able to change either requirements or sort of those early elements of the architecture to be able to address them. Once you're locked into more of a solution, then you have to start looking at, like, how do I patch this solution, or what other security controls can I apply on top of this solution, right? The idea of like a security technical implementation guide comes to mind, right? Most people sort of just assume what operating system they're going to use, and then they apply controls on top of it, right? However, if we can, look earlier on in kind of like the requirements and architecture stages, you could maybe completely avoid some of those threats outright. So we'll talk about it a little bit later, but there are sort of different methods that are more apt to these different stages, right? So the same modeling and like threat analysis methods that you might use in the design stage might not necessarily be applicable in the requirements stage, just because of the amount of information that you have. So again, we'll talk about that in a little bit, but the other point I wanted to make, though, before we left this slide, I know with MBSE, one of the terms that gets thrown around a lot is single source of truth, right? But interestingly, here you show multiple different models, right? And kind of talked a little bit about their overlap. So I know we mentioned that models should be built for a purpose. Can you talk about how or why you might want multiple models, and how does that work with that concept of still having a single source of truth?
Okay, yeah, very absolutely excellent point. Single source of truth and multiple models does not contradict each other, because the model is building for a purpose, and this purpose can be the main of a system or a specific stakeholder view. For example, you can have a model specifically for for simulation of the subsystem, because you want to simulate in more details or different way of critical subsystem, where other system can build based on already known technology, or for your organization, for your overall business, it's already very well known problem or solved problem, so you don't need to know much more details. But for one specific subsystem, you want to build something very detailed, high fidelity, maybe on a level of digital twin, and you simulate it. And for this subsystem, it will be source of truth. Another model that, for example, cover the business architecture of your system, it will be for that aspect of your system, it will be single source of truth. So you already have a number of the models. You can have models specifically built for risk analysis, and it's not necessary that it will be network architecture model, which can be very different. It's need to have different attributes, different type of taxonomy underneath, right? So the specialization of the model is very important, and more domains, more aspects, more complexity you have in your system, more types of models you will have in your portfolio.
Yep, and we'll talk a little bit more about that complexity as well.
Yes,
coming up.
yeah, exactly. It's very very permanent point, because one of the benefits that people looking to have from MBSE, it's managing complexity, and it has the ability to do that. Again, it depends of implementation. There is some unreducible complexity in the models because your system is complex, so your model will be complex. Even its simplified view of your system, like model is always simplified view of your system. But there is sometimes people add additional complexity to the model that it's not necessarily need to be there. But this is nuances of how people implement it. So what do we want to talk about?
Sure. So we talked about sort of MBSE, and we talked about the models, which are going to be the output. But if we take kind of a step back and look at the role of a systems engineer when it comes to security analysis and design, which we were kind of talking about in that last slide, really it's about coordination, right? So just as a systems engineer is going to be coordinating across other engineering disciplines to make sure that we're still hitting those cost, schedule, and technical requirements, right? The same thing for kind of this subset, which on the chart is systems security engineering. And so, again, we're going to be coordinating across a bunch of different security specialties, right? And so the systems engineer is not necessarily going to be diving into evaluating particular products that are going to be part of maybe a solutions architecture, but they'll be coordinating with those teams or those subject matter experts to understand, okay, if we go with this particular solution architecture, what are the implications for some of the other parts of the system, right? And so what we're going to focus on sort of for the, I think, remainder of this is one of those other specialties listed, right, which is threat modeling. And one, I think, that's maybe a little bit more applicable to the systems engineer because it's going to help to influence the architecture and design, maybe more so than some of the other more specialty parts of that system security engineering.
Yes, so system engineering covering, like you mentioned, the other aspect of engineering, and has a way to influence it. Definitely need to be aware of cybersecurity needs of the system and understand the methodology that should be applied on different stages of software development or system development, and what they specifically can do on the early stage, because they have most influence on the early stage of development, like requirements. So I hope that what we offer here, even with threat modeling, can help system engineers to be a little bit more aware and have some kind of tools at their disposal to start to work on that. And like see how the threat modeling, even it's not explicitly related to, for example, creating requirements, it's definitely should be one of the methods that influence creation of cybersecurity requirements for a system. Because if the threat identified, it's need to be kind of reflected in the requirements to mitigate it. So we will talk about that later.
Yeah, so whenever we're talking about threat modeling, right, really it's going to take different forms at different stages of the system's life cycle. And so it's going to look slightly different, whether you're very early in the process, kind of in your concept of operations, sort of like formation phase, versus if you have a system that's already operational, your threat modeling, or maybe a better term at that point is threat hunting, is going to look very different. And so I mentioned earlier about how the model-based systems engineering and focusing more on model views rather than diagrams is going to be helpful, and we can adapt some different threat modeling methods to leverage those models. So here we have a bunch of different threat modeling methods listed, and so we don't have nearly enough time to kind of go through all these in depth. I know, Natasha, you have a blog post kind of giving some of the highlights of these different methods. But I'll just kind of point out a couple and talk about how they are applicable to the different stages, right? So one that I know we're going to talk about a little bit more, and it's at the top of the list for the reason is stride, right? So stride is a mnemonic that tells you about the different types of threats you might face. So spoofing or tampering, right? And stride traditionally is based on data flow diagrams. So you might have a database represented, and then that database might be being queried by an API, and you would just draw out all of those different system elements and the flows between them. And then applying stride, you're able to identify different threats that might happen either to those different elements or to those different data flows. And so while we're not just drawing data flow diagrams, whenever we're creating a model, there are certain views, such as like an internal connectivity diagram, that are amenable to doing sort of a similar process of identifying either different components or different connections that have the same types of threats that you can apply. So again, whenever we're talking early on in the systems development lifecycle, I think stride is fairly applicable, right? However, later on in the life cycle, if you have a system that's operational, let's say your model of that system is very fleshed out, then we can start to get more specific, right? So CVSS, right, is a vulnerability scoring system that looks at specific vulnerabilities in specific implementations of some service or some software, right? You're not generally going to have that sort of information early. However, if you have, say, a software bill of materials that you can generate, you might be able to model using CVSS a little bit easier, right? Or, and again, any of these modeling methods that require, say, like state machine diagrams, you might have that early on. It'd be nice to. However, you would definitely have an enumeration of all possible system states if you have an operational system, right? So again, a question that I've gotten before is, how does threat modeling with MBSE differ from, my favorite threat model, whether that's Pasta or Linden, right? It doesn't necessarily differ. What we're doing is adapting one or maybe more of these threat modeling methods to use our model as its basis for generating threat scenarios.
Yes, and I want to kind of emphasize that some methods that you can't really use the model to do anything, but you want to do threat modeling with this method, but you want to document result of your threat modeling with this method in your model because it may reveal some insights that it's not obvious. For example, like persona non grata. It's persona non grata, you do analysis of potential threat actor, of adversary, and it's very little information you can draw from your model, maybe except like business capabilities, something like that. That when you make the profile of potential threat actor, you want to introduce into this model and start to think where this actor can actually harm your system. You can look and if any of the threats you already identified with other methods, you can attribute to this kind of threat actor. So this is where multiple threat methods works together. Mm-hmm. And they come together specifically in the model. And it will give you even more insights to these to your security posture of your model, how your system is secure, less secure, or more secure. So I would suggest that people look at all of the methods and evaluate and see what combination of the methods can be helpful in their situation or their system. And like you mentioned, Alex, that they can be applied at different level in different phases of the software development cycle.
Yeah, I would say also one other consideration when we're talking about this process is also look at the personnel that you have, right? So some threat modeling methods are heavily driven by subject matter expertise, right? If you have someone who is a threat subject matter expert, definitely leverage them, right? Like use a method that plays to their strengths. However, I believe that we got a question before this webcast asking, who should be doing threat modeling? Well, of course, subject matter expert on the system that knows the threats to it, maybe like a network operator, right? They would be a very good candidate to have input from. However, I think some methods also are more amenable to maybe folks that don't have as much subject matter expertise, but because they provide slightly more structure, it allows you to kind of run with the model a bit more than having to have that in-depth like expertise in threat modeling.
Yeah, I agree. Let's start with go deeper in threat modeling.
Sure. So we talked about all the different methods on the last slide, but this is kind of I'll say generic process that I think is adaptable to quite a few different methods, right? And it consists of 4 questions that we need to answer. The first one being, what are we building, right? And this is going to be captured within your systems model. Second off, in general, whether we're doing very high level conceptual threat modeling or we're doing hazard analysis, right? We're basically asking the same question of what can go wrong, right? And so we'll talk about those throughout the rest of the presentation generally as threat scenarios, but for those that are familiar with, say, like hazard cases, we're talking about the same thing. What can go wrong with our system, right? The third one is, okay, now that we have an enumeration of everything that can go wrong, what should we do about it, right? So this gets into some of your risk analysis, applying security controls, right? What should I do to prevent this? Should I even try to prevent this? Is this just something that we can accept as a risk, right? And then finally, the fourth one, unfortunately, I don't think we're going to have quite enough time to get into this one today. But did we do a good enough job, right? And that's going to be our validation of our threat model. So again, I think this general process is applicable to almost every method that we had on the last slide, but one question hopefully we'll answer in the next slide that people might have is, well, if it's such an easy process, why do I need a model to do this? I think I could get away with diagrams for this. And so the answer, and I think we hinted at it a little bit earlier, right, is system complexity. So on the right side here, we have a graph showing the number of lines of software in military aircraft, right? And you can see that it is taking off kind of exponentially. And so as you introduce more lines of code into any sort of system, right? As you bring in more third-party software or open source software, right? You're opening up more interfaces. You're going to have more of a chance of introducing vulnerabilities and then having threats that seek to take advantage of those, right? On the right side here, again, this is kind of an eye chart. Maybe don't try and read it, but this is the highest level view that we have of the DevSecOps process, which we published as part of the platform independent model. And you can see that this process, just describing how one, creates, tests, and then releases software, is incredibly complex. There are many different interactions between the different processes, many feedback loops, right? So whenever we're seeking to model threats, we are going to need to evaluate all of those different components, all of those different interactions. And that's why you can't just get away with a diagram, because if you tried to annotate, say, that diagram on the left, that view on the left with all of the threats, it would probably become about unusable.
Yes, and each of these boxes has at least 2 layers in deep. Some of them even 3 level layers in deep. So this complexity, this is just on the surface. So it's even more threats, even more annotation that literally not possible to do on a diagram, and only on a handful of diagrams. So that's we need the model.
Can we ask a quick clarifying question from Mike saying, can you explain a little more for the attendees the differences in systems level threat modeling and software threat modeling?
Sure. So one of the biggest ones I would say is when you're looking at the system level is what threats are you inheriting, right? So depending on the business that you're in or the environment that your system is going to be deployed in, there are threats that just come along as a result of your mission or your business case. So that's one of the biggest ones is the threats that are outside of just like a specific software vulnerability, right? Natasha, would you want to mention any more on that?
Yeah. So in addition to that, like it's inherent threats. When we talk about system, there is also the organization that supports the system or builds the system, and it's introduces threats by themselves, including insiders threats and the supply chain threats that is influence your system, how it's behave, how it's built, and it's not on the software side. Software, it's vulnerabilities and threats on specific part of software. Again, systems doesn't mean that your software exclusively system. You can have cyber physical system. So you have hardware, you have embedded software. Yeah, so there's other aspects more in addition to software to consider when you talk about this level of systems.
Thank you for that. Yeah.
Sure.
Yeah, so hopefully we've convinced you on why you need a model. For the kind of remainder of the presentation, we want to talk a little bit about now, how do you integrate that kind of four-step process that we talked about of threat modeling into the rest of your model, right? And so what we're showing here in this graphic is our way of integrating all of the different constituent pieces of threat modeling into, in this specific case, the unified architecture framework. So again, based on UAF ML. However, most of the elements that you see here, even if they are inherited directly from the unified architecture framework, it doesn't necessarily mean that you could not have a similar profile that you use to capture threats, attacks, and all of, again, the constituent pieces also built out in another language like SysML. Would you like to talk about the profile a little bit more?
Yes. So this profile, it's based, like Alex mentioned, based on UAF, and it's utilized. We try to utilize as many original elements as possible. So extension is minimal, just necessary to do threat modeling. Especially in the method that we developed, pretty structured, how to put the threat scenarios into the model. We added one more profile. It's not in the slides, but we will cover. Probably I should mention with the workshop later in August. We will make the profile that cover RACI matrix that is accompany these threat modeling profile and showed a lot of benefits, especially for internal threats analysis. And it's relatively simple to implement. First of all, because it's just few elements added, but it's pretty sufficient. We applied it in a couple of cases, including live projects. So we proved that it's working and it's does what we want to do.
And so the only other thing I'll mention about the profile here, one of the key pieces, and this is really what is going to amplify our threat modeling versus diagramming, right, are in the relationships between, say, our threat elements, our threat actors, particularly the attacks which realize a given threat, right? So if folks are more familiar with the term vulnerability, right, you only have a vulnerability if there's a way for someone to exploit it, right? And so whenever we're talking about threats here in our threat modeling, we also need an attack that's going to substantiate the realization of that threat, right? So we need both that threat actor, someone who's interested in causing harm, and then the attack that actually enables that, right? And then additionally, as we'll get into a little bit later, we also have relationships to security controls and security requirements, right, which are kind of more the bread and butter of our systems engineers. So
yes, now we will talk a little bit how we use it. Yes, so this is a diagram. It's a result of threat modeling analysis on a process, a DevSecOps process. And you can see this is the process itself. And this is all kind of roles in your system that has any role in and life cycle of this activity. In blue, you see the threats we identified, and pink, we identify the attacks. It's essentially the method that attacker can use to realize the threat. And the orange here is a threat actor. Like you can kind of read it as a sentence, like this threat compromise this asset. So in our analysis, the process was this asset, not the component, which is make it a little bit different from like a basic stride, for example. The same as here is this threat realized by this attack. So this threat need this method to be realized. If there is no method, threat, maybe not a threat. If you can see the inside that the model, this way of modeling that they gives you immediately, this is software developer that actually performs this process, but the same actor is actually can cause this threat. So you won't see this relationship, this inside, if you don't put all of this in one diagram, implementing the just good system engineering analysis and the threat modeling, and you put all together and you see that your software developer can be insider threat for your asset. So this is the kind of combination of all things on one place. But if you can do this analysis for any asset, you will realize how many threats you have and which one you need to mitigate, analyze, prioritize, and mitigate later, and find a solution for that. Anything you want to add before we go?
Yeah, so
Analysis?
the only other thing that I'll add, because we were talking about having multiple models and how we need to substantiate our threats with attacks. One of the nice things here, we can actually use or federate models. So your attacks, you can actually source a lot of those from open source frameworks, right? That enumerate all sorts of different attack patterns. So you can have those as a common model that could be used across multiple systems, right? And then as you import those, then you're able to substantiate specific threats to a specific system with sort of these, I'll say, more generic attacks, but also attacks that are, validated, agreed upon, kind of by the community. So the advantage there is if you're using standard attacks or standard attacks within your model, you can also implement sort of standard security controls that are known to help guard against those attacks.
Yeah, community. In this project, we use CAPAC attack taxonomy. It's MITRE the CAPAC taxonomy. So we use it for high level threats, and from there we can trace to MITRE attack taxonomy and to standards security control mitigations from NIST. So that like really helps beef up your threat modeling method, and you rely on the knowledge, on the wisdom of a community to help you to solve your threat problems with like already proven solutions.
Yep, good point. So far we've mainly showed diagrams or model views from our models, right? However, I mentioned that a lot of the power comes from those relationships, and then additionally being able to generate other views from your model based on those relationships. So again, quite a large chart here. This one is showing all of our system requirements across the x-axis. And then on the y-axis, showing all the processes that we need to conduct to satisfy those. So again, this particular one is pulled from our model of the DevSecOps process. So you'll have requirements like needing to write code, and then you'll have the processes that support those. And so, again, this traces our requirements to our processes, but Natasha, if you go to the next slide, we can also, on the right here, trace our processes to threats that might impact them, right?
Mhm.
So we showed on a slide earlier that traceability line, right, through all of our different models. This is where we also want to be able to trace from requirements to processes to the threats that might affect them. And key, it might not come out as much in these matrices or the tables, but hopefully on the left, we can show how there is generally going to be a multiplicity of threats to attacks that can realize them, right? Generally, there's more than one way that you can cause sort of the same issues to manifest within your system. And then additionally, there are generally going to be multiple different security controls which are going to mitigate a particular threat. So again, it's not necessarily a one-to-one on threats, attacks, and security controls. And key, especially for the systems engineer, right, is going to be identifying which security controls do I want to select, and which are going to fit the best with the rest of my requirements, right? Because every security control that you implement is going to have some uh, cost to it, whether that's in performance or actual monetary cost. And so again, we need to manage those along with sufficiently mitigating our threats. So hopefully these two charts kind of show that.
This is everything we want to talk about. I think we have like time for 1 and 2 questions.
Yeah, maybe we work on 2 questions. First one, I know you mentioned a workshop in August. Can you give a little quick plug to that? Maybe like, are you still looking for speakers or what's on the agenda for the workshop?
So workshop, it's actually what we, Alex and I, we will go deep into this method with like showing how to do that, how to do the model. We will have hands-on activities on the threat identification of threats, threat models, and modeling, and how to put them actually in your systems model or your architecture model. I hope people will find insights. So it's actually covering like a little bit of basics for MBSE, because we need to do some kind of modeling. You need that, and then basics on threat modeling, and then how to bring them together. So it's 1 day, one whole day activity with hands-on works in groups. And we're doing it for 2nd year. Last year it was just half day. This time it's more hands-on, more involved. We look forward to see people there so we can talk with show how this method works.
Great. So I added a link to the chat so folks can take a look at that. Let's just end with this one. We mentioned we got a couple questions prior to webcast. Terry asked, how can we better integrate threat modeling into MBSE early on, especially for complex systems like federal or hybrid cloud setups, so security risks are identified and addressed before they surface downstream? We got a quick answer to that?
Yes. So it's if there is any MBSE already in the program, it's mean that the additional activities on specifically threat hunting, or not threat hunting, threat identification early stages need to be introduced into the whole process of like modeling. People need to start like from the requirements and have specific security requirements when they do requirements models. And then as soon as they have any conceptual architecture of their system, they need to look for threat modeling method and start to work on that level. So as soon as it's introduced, it's encoded in your formal process for your system engineering, then you will do it. If it's kind of optional, if people need to do it like in free time, it will never happen. It's need to be encoded in your official process for system engineering and architecture.
Great, Natasha, Alex, great discussion today. Thank you very much for sharing your expertise. Last, we'd like to thank you all for attending today. Upon exiting, please hit the like button below and share the archive if you found value. Also, you can subscribe to the SEI's YouTube channel by clicking on the SEI seal in the lower right corner of the video window. Our next webcast will be July 17th, and our topic will be identifying AI talent for the DoD workforce. Registration information is available on the SEI website now and will be emailed out as well. Any questions from today's event, please send to info@sei.cmu.edu. Thanks, everyone. Have a great day.